Thank you for the invitation. I've been coming to this conference for many years now, so it's a bit strange to be on this side. So I'll be talking about my latest and ongoing work with Michael Abbott on ADS3 integrability. So the idea is we have all these correspondence. We have the ADS-CFT, we have integrability playing a role in ADS-CFT, and why is this, even though we don't have really numerical data, it's very important that we have all these correspondences and dualities because we actually are able to check our results. At least we make a prediction on one side of a duality and we can actually check on the other side of the duality. And in fact, for ADS3, what happened 3 years ago is that the classical test of Hernandez-Lopez failed. And for 3 years, this was an outstanding problem. The main thing is that, so when we set up to do this problem, we weren't really sure which side of the problem, either it was in the integrability side of the beta ansatz or in the Worldsheet calculation. We tried many things, and finally, we actually understood the problem. So the Worldsheet calculation is actually correct, but the beta ansatz actually needs to be implemented with some corrections, which are finite volume, and typically in other cases of the ADS-CFT, they're exponentially suppressed, but because we have massless modes in the ADS3, they stop being exponentially suppressed. So this is going to be basically what my talk is going to be. So ADS-CFT and integrability, the prototype, of course, is 4-dimensional n equals 4 superring mills and strings in ADS5 process 5. Classical integrability in that case can be seen from both sides. Either we check loop by loop the Young-Mills case, and we, from a spin chain approach, we can actually calculate the beta ansatz and get to classical integrability, or from the coset action and symmetries, we can actually build basically an infinite set of conserved quantities, Lark's-pair, the monodromy, and the finite gap equations directly, and get to classical integrability. But today, actually, what I'll be talking about is, of course, not n equals 4 superring mills and ADS5 process 5, but I will be talking about another example which has less supersymmetry, which is ADS3 integrability, which is basically strings are on either ADS3 cross S3 cross T4 or ADS3 cross S3 cross S1. So we again have a finite dimensional subalgebra. We can build a coset, and from that coset, in the same way as ADS5 process 5, we can actually build a Lex connection and determine the S matrix either from the symmetries, and also get a no-loop beta ansatz, which for a long time was known for the massive sector, and as we've heard this morning, for including the massless sectors as well now. And so what is new that I want to discuss today is the fact that if you study the modes or excitations around the BMN particle, what you find is so massive excitations. So this alpha here is, as Olaf mentioned this morning, so each one of these spheres will have a particular radius which is given by alpha, or 1 minus alpha. But in particular, what I'll be looking at is ADS3 cross S3 cross T4, but everything that I'll be saying could, in principle, be equally done for the other case. And what we have is, indeed, 4 bosonic massless modes and 4 superpartners because of our T4 directions. And talking about massless modes, so the biggest questions is, which role do they play in integrability picture? A lot of what we've heard this morning was exactly to address this. And also is, okay, we have the Worldsheet theory, and so we have now this integrability picture. And can we actually use the classic tests of integrability to, in this particular case of ADS3? So in terms of comparisons between the Worldsheet and beta ansatz, we take the case of a classical spinning string at strong coupling. And from the Worldsheet, we can determine the one loop energy correction. What we do is you perturb the solution by some mode fluctuations, and you determine the frequencies of those fluctuations, and then to determine the one loop correction, you basically sum over the frequencies. You actually need to be careful about how you sum these frequencies, especially because you're analyzing the solution for large spins. And so you need to basically regulate your solution, and you end up getting a correction. From the beta ansatz point of view, you can also expand the beta ansatz to order 1 over h, meaning you start with the beta ansatz where you have a matrix part of the S matrix and some dressing phase. The dressing phase typically is given the leading part by the typical AFS phase, and then some subleading correction with the coefficient C1, and these are basically the conserved charges. And what you want to calculate is actually what is the correction to the energy, and the energy is basically, it's Q2. What is the correction to the energy coming from exactly this perturbation in the dressing phase? And if you do that, if you expand the dressing phase and you expand the charges, you can actually calculate exactly the correction for this energy. And this is going to correspond to the non-analytic part of this one loop energy correction. So in particular, we'll work not with general classical spinning strings, but we are going to restrict ourselves to the case of R cross S3. This is a consistent truncation, and the simplest solution in R cross S3 is just the circular solution. It's a macroscopic solution wrapping all around the S3. It has two charges, which are very large in the two directions, two circles of the S3. And what happens is if you calculate for this solution both the corrections in the Worldsheet and in the beta ansatz, you find that they don't agree. They're different. So this was the classic test of Hernandez-Lopez in 2006 for the ADS5 process 5. It agreed perfectly there, and in this case it doesn't. So what I want is actually to set out to not only, okay, I just gave a brief overview of the two calculations and the fact that they don't agree. I'm going to explain in a bit more detail each side of the calculations for the circular strings, and then I will explain what we found as being the reason why these two solutions didn't match. And this is going to be when I'm going to introduce the massless Luscher corrections and explain a bit furthermore what are the things that are completely correct and what is still open problems in the calculation of the massless Luscher corrections. So we start with the circular spinning strings on ADS3, S3, T4. And again, I've written down the solution at charges, the Virasoro constraint. And the main thing that I want to point out is actually that if you looked at the algebraic curve picture, this is a very, very simple solution. It's just a one-cut solution. And it's the simplest solution we could actually be studying from the algebraic picture. And this is what we're going to do in the beta ansatz. So, but first, let's focus on the Worldsheet calculation. You can actually calculate all of the frequencies. What you do about calculation of the frequencies is, well, you calculate bosonic modes. The bosonic modes are in S3, which are exactly the same bosonic modes that existed in S5, but now we only have S3, so there's two extra bosonic modes in S5 that are not in this calculation. Also, we have bosonic modes in ADS3, again, 2, while ADS5 had 4, which have mass kappa squared. What do you have new now? In terms of bosonic modes, we actually, instead of having extra modes like we had, massive modes that we had in ADS5, we now have 4 massless bosonic modes, which correspond to the T4 directions. And then we have all the superpartners. We have the massive fermionic modes, which are 4 now, instead of the ADS5 cross S5, 8. And we now have the superpartners of these massless modes, which are massless fermionic modes, which are 4 as well. So the main idea is that, okay, now we have all the frequencies. What we can do is we can sum them. We can sum over all modes in these frequencies, and sum over all different modes and all the different mode numbers. I wanted to point out that when you do this calculation from the worldsheet point of view, the sum in some way the wrappings, the sum of modes around the sphere is built in. You are summing. Basically, there's no question about these wrapping corrections from this semi-classical point of view, because you are doing fluctuations that actually go all around the sphere. And this mode number n is exactly the number of times the fluctuations go around the sphere. So because we're interested in the circular strings for large J, we want an expansion in J in the end, and this sum needs to be regularized. This was done the same way as in ADS5. And you can actually determine the regular part in this expansion, which is the part that is going to match, or should match, the perturbations on the dressing phase, the one loop perturbations on the dressing phase from the beta ansatz point of view. So if we do all of this, we get the final result, which is an expansion in J with these coefficients. So we have our worldsheet result. So what happens on the other side now of the beta ansatz? R cross S3 is basically the SU2 sector of the beta ansatz. And as it happens, if you take the beta ansatz in ADS3 cross S3 cross T4, the SU2 part is a consistent truncation, the same as R cross S3, and you can write the beta ansatz exactly the same way as in ADS5, with the difference that the dressing phase can be different. So this is, again, this describes strings on R cross S3. Because we are in the SU2 sector, the dressing phase is basically the massive scattering dressing phase, which Olof mentioned early this morning. And so this theta, basically, it's the expansion of the dressing phase. Again, you have the regular AFS phase, and then you have your perturbation, one loop perturbation of the dressing phase. And now what I can do is basically follow exactly the same procedure as Hernandez-Lopez for circular strings that was done in ADS5 cross S5. If I indeed do that, I can actually define the resolvent by basically putting poles wherever there's roots, there's beta roots, and then integrating over the cut, a single cut, with some particular root density. And what I can then do, in terms, if I look back at my beta ansatz, I can take the logarithm of the beta ansatz and transform any sums, which here are products and then are sums, into basically integrals by using this density of particles. If I do that, so the log of the bit equations after reusing what the resolvent is, I can actually write it with this, where the resolvent, it depends on the resolvent and the charges of the solution. And the resolvent in itself, actually, if we expand it in X here, if I expand it in X, the resolvent also basically is defined by the charges. So this is a notation of Hernandez-Lopez. In most of the papers in ADS3, you're going to see actually the dependence on X and not on this X tilde, and we on purpose put X tildes just to separate the two notations. So the actual resolvent for the circular string is given by, again, by the one cut solution, and it's given by this expression. And we can actually expand this resolvent into the charges. So we expand it in X, and we get all the conserved charges, classical conserved charges. And in particular now, because I assumed that my dressing phase had the perturbation, what I want to do now is perturb also my charges. and I want to calculate the Q2, the variation of the Q2, which is the variation of the energy due to the dressing phase. And in fact, if you do the K equals to M, K is the mode number in the beta ansatz, actually the beta ansatz dramatically simplifies, and what you find is basically a closed form for Q2, which is very easy to write, and it's basically this expression. So if I know what all the charges are because I know the resolvent and I know this expansion, and as an expansion in J, actually the predicted one loop energy correction is going to be given by this in terms of the coefficients C1. So in ADS5, actually, wherever the coefficients had a 1 here, it wouldn't appear, but in ADS3, these are going to be part of the solution. So again, if I do know the one loop energy correction as long as I actually know my coefficients C1. What Hernandez-Lopez did in 2006 was actually, okay, we know the result for the circular strings from the Worldsheet. We have this prediction, we can actually calculate the coefficients. And they calculate these coefficients, which then can be thoroughly checked via crossing, Magnon scattering, BMN. So it's been thoroughly checked, everything agrees perfectly. So now what happens in ADS3 cross S3 cross T4? What happens in ADS3 cross S3 cross T4 is that you can actually calculate these coefficients. Let's not talk right away about comparing it to the Worldsheet. There are several ways of calculating these coefficients, and it was actually calculated either by crossing symmetry or by the semi-classical Magnon scattering. And they both obtained basically these coefficients here. So if I use these coefficients inside here for the predicted one loop energy and I subtract it from what I found from the Worldsheet, I find a mismatch. So the difference is actually given by this function. This can be expanded in J, of course, but this is exactly the mismatch. Of course, these coefficients have also been checked by BMN Worldsheet scattering. And what happened if I try to do the same thing as Hernandez-Lopez did? If we did the same thing as Hernandez-Lopez, what we would obtain for the coefficients were actually just this part here in black, but with R and S able to start in 1. But this extra part is what forms the mismatch. But of course, these coefficients have been checked. They're the correct coefficients. So what is the source of this mismatch? So this was the problem that we did set out to explain a while ago. And again, for many times, we weren't sure whether the mismatch was from the Worldsheet point of view, if it was from the beta ansatz point of view. And in the end, we actually found out that this mismatch had to do with finite volume effects. And to actually study the finite volume effects, we're going to go back to the original calculation by Luscher, which does exactly this. So it starts from an infinite theory and then calculates finite volume corrections to the results. So finite volume effects. We start from Luscher, the original calculation by Luscher. We start from a relativistic 1+1 dimensional theory with particles of mass m, s. So the mass s is assumed to be exact. What do I mean with this? It means that it's already renormalized with every diagram that you could think of that is in infinite volume. So we've already taken into account every diagram in infinite volume to the point that whenever we go to finite volume, any corrections that show up have to be with particles that actually travel around the finite volume. And that's what Luscher corrections actually are. So this is the dispersion relation for the relativistic particle of mass s. And so this is infinite volume, and now we go to finite volume, and we want to determine just, as I mentioned, the contributions from diagrams where the propagator wraps the space L. So the leading term is actually when you have one propagator, one vertex here, sorry, not propagator, and it's basically given by this, and you can see here an exponential proportional to the momenta, which actually is why the Luscher corrections typically are exponentially suppressed. Moreover, I'm doing finite volume, but I'm still taking the volume to be large. If I do this, the virtual particle that I was wrapping around the cylinder actually becomes on shell, and this vertex can be substituted by the S matrix. In terms of the rapidities, this is the shape that it comes, and you can see that this exponential actually has the mass there. So these results, once you do this integration, are always going to be exponentially suppressed when the mass is non-zero. But what happens when the mass is zero? And if you look at this drawing, you can actually see that this drawing is exactly the same as what Alessandro had earlier today. So if you have a mass S and you plot the energy with respect to the momenta, you see that, meaning no matter what, this exponential will always be exponentially suppressed, because what's here is basically the energy, and the minimal value that it will have is S. But what happens when the mass is zero? When the mass is zero, this exponential, which is, well, I shouldn't look at here, I should actually look down, then back at this original result. If I look at the energy, what happens is that this exponential is still exponentially suppressed, you know, for any distance, finite distance from the momenta equals zero. But when the momenta equals zero, or very, very close to it, what's going to happen is that this exponential will be of order 1. So for true massless particles, there will be some part of this integral around this area where the contribution can be not exponentially suppressed, and can be actually of the same order as the other, as the beta ansatz. So what happens in ADS, CFT? What happens is actually the dispersion relation is changed now. The Luscher correction, the first Luscher corrections can actually be calculated, and they're basically given by this. This is some Jacobean. It was done by Yannick and Lukowski a while ago. And what you have is basically a virtual particle traveling around the cylinder, and then one real particle traveling in time, and you have the S matrix between the two of them. But this is for one particle. For circular strings, we actually have K excitations, where K is of the order of L. And for that, we need the multi-particle F term of Luscher. And that was actually derived from TBA and by Beinok and Yannick. And what you can do is, so you can actually calculate this multi-particle F term, and now what you have is a product of K S matrices. This is extra terms that come, there are parts of the beta ansatz, and actually for our case they're zero, so we won't be concerned about them. Now you have a set of physical excitations, and you have one particle traveling around the cylinder. So what type of matrix do we want here? Well, what we want is the mixed mass S matrix, so the scattering between a massive and a massless particle. And this is one of the matrices that were introduced early in this morning. So, and this is what will go into our calculation of the multi-particle F term. So mixed mass S matrix for our case is basically given by, it has a matrix part, it has the dressing part. The matrix part is given by some coefficients, which in our, if we expand the variables in L, both for the massive and the massless, we can actually expand each one of these terms, and they're basically very simple as functions of L here. And this is what I'll define as theta, just for future reference. This is the matrix part. Of course, you also need to do the same thing for the dressing phase. And what you actually do afterwards is you calculate the product of the S matrices from here. So you have here a product of S matrices. From the beta ansatz, what we did when we had a product of factors, we actually took the log, and we then turned the sums into some integral via the density of roots. What we do now is basically the same, but first we need to exponentiate and then do exactly the same procedure. One thing to note is if I multiply the exponential times the dressing phase, both of these two terms are actually, if I expand them in L, both of them, as you can see, are going to be proportional to the momentum q. And this is, again, what I had just mentioned, that when the momentum is 0, this exponential stops being exponentially suppressed and becomes of order 1. So this is why, exactly, that the part of the exponential is, you can actually calculate, expand it, and it comes proportional, the exponential comes proportional to the momentum, where phi is just some expression that depends on Q2 and the coupling G. So this is the ingredients we used: the mismatched S matrix, the dressing phase, which we assumed was just the regular AFS. We integrated over all physical modes. I wrote here what theta and phi are, meaning this is the S matrix, the total part of the S matrix. And the energy correction, we can calculate the integral once we plug in what this exponential is. And you can actually get a nice analytic form in terms of theta and phi, expand it in J, and this is what you get. So recall that the difference of the mismatch that we're trying to explain, is of this shape. You can see that the powers of J agree, but the coefficients don't. Two things we can learn about this. So we actually get the correct powers in J. What does this mean? That the Luscher terms, which in ADS5 process 5, these finite volume corrections that in ADS5 process 5 were exponentially suppressed, are no longer exponentially suppressed. They're of the order, of the exact same order in J. They're leading. So the SU2 beta ansatz equations basically are not enough. We need to include this type of corrections. On the other hand, we don't get the correct coefficients. So what are we missing? So no matter what we're missing, what we've managed up to now, even if I stopped right now, what I managed to do is to check that these corrections cannot be ignored when you calculate, when you're doing a beta ansatz calculation. So in fact, I wrapped my particle once around my cylinder, and I got a not exponentially suppressed correction. What if I wrap it twice around the cylinder? What if I wrap it 3 times, n times? If the first one was not exponentially suppressed, neither of the other ones that typically would be twice exponentially suppressed, 3 times exponentially suppressed, they're not going to be exponentially suppressed. I need to add them all. So it's not enough to consider one virtual particle going around the cylinder, but I need to consider winding around the cylinder n times and sum them all. This was actually done by some mode expansion in 2008 by Heller, Yannick, and Lukowski, where they obtained this expression. But this is still for just one real particle, one massive particle. For the circular strings, we need k of them. But in fact, we can actually guess what the generalization of this expression would be for a multi-particle state. And this is what we're going to try next. So we have a sum over all possible windings of a virtual particle winding around the circle. What goes into the calculation? Exactly the same things. The same S matrix. We integrate over the physical modes. We sum over all modes, winding modes of the virtual particle. And we get some much more complicated now energy correction. And if we calculate this energy correction either by some identities or just by expanding in J, we get extremely similar result to what we get in the mismatch. Actually, meaning if you don't remember, actually there's an extra factor of 2 here. So we get the exact same form up to a factor of 2. So still not the exact result, but it's almost there. Why would this be not the exact result? So before I go further into this factor of 2, which I'll mention again, another thing that we can still do is actually study other semi-classical solutions. I focus on circular strings. So which other solutions have mismatches? Well, the solutions that have mismatches are the circular strings, as I mentioned, SU2, The SL2 sector also have mismatches, and these are cases where the excitations are actually of order of the length of my space. But SL2 short-folded string, which the excitations are large but less than the length, and the giant Magnon solutions, where the excitation is just 1, both of them actually agree between Worldsheet and the Bethe-Ansatz calculation. So we could actually perform the same calculation, and our best guess at the moment is that the difference between these two types of solutions is actually because of the number of excitations. The regimes are actually quite different, and for the circular strings, you're talking about the number of particles being of the same order as the volume of the space. Now I wanted to mention, again, go back to this factor of 2. So how can we actually deal with this factor of 2? Well, there's many things that we basically took as our starting point, many assumptions, which if you start actually fiddling with them, they might change your result. In particular, the S matrix, the phase of the S matrix is constrained by the crossing, but it's not completely determined by the crossing. So in fact, if we allow to play a bit with the dressing phase, and with the AFS dressing phase, for example, put some string frame factor and type or factors of that type, actually we can get rid of the factor of 2. But the point is, as it stands, we made an assumption that a particular phase was to be taken, and by doing that, we got the result up to a factor of 2. So other things that we did check, but it's not completely, we did check to up to a point, but not thoroughly, is whether, so there's other types of corrections from finite volume, which are mu terms from Luscher. We did check that they seem to be actually exponentially suppressed, but further checks should be done to confirm this completely. And also, we assumed the massless dispersion relation that is fixed by symmetry from integrability. But in fact, we know that there is a mismatch between the dispersion relation from integrability and the dispersion relation at BMN at 2 loops. Even though this should give some higher order corrections to our calculation, this is something that cannot be also ignored. But we actually, what we did was we took one virtual particle and we wound it around the cylinder n times. But there are other things, there are other types of corrections that can happen, meaning when you're doing Feynman diagrams, you have many different types of corrections, and in particular, you can have something that is proportional to like 2 loops, like this expression, where you can see here, instead of 1 integral, I have 2 integrals. This type of corrections were not considered in our calculation, and can, in principle, in different calculations, return a result, a different result, and change the coefficients. So we might need a better derivation of the wrapping Luscher terms for n greater than 2. In particular, actually, a more careful look of the TBA, we can see that in our mode number expansion, there's a -1 to the n that needs to be included. But in fact, actually, all odd corrections in the circular string case cancel out. So for our calculation, it doesn't change anything. Also, in weak coupling, there's the next to leading order corrections that were done, and the way how to adapt these to strong coupling, meaning they obtained corrections that look very much like these corrections that are written here. But the way how to adapt them to strong coupling is not direct. Finally, of course, all of these corrections should be included in full TBA, but the problem is that the TBA needs to include mixing between the massless and the massive sector. And as far as my understanding goes, you have massless TBA, you have massive TBA, but they typically decouple. And we don't have a TBA that actually could mix the 2 sectors. So finally, I will finish with some summary. So the problem that we addressed in our work was the outstanding mismatch of one of the most classic tests of integrability, which is the one-loop dressing phase in ADS3 cross S3 cross T4. We concluded that the beta ansatz is insufficient to describe the spectra of circular strings without including wrapping corrections. Why? Because of the massless modes, and because we saw that the finite volume corrections with the massless modes are actually not exponentially suppressed anymore. Also, just to stress, the Worldsheet correction has built in these wrappings, meaning the way you do fluctuations has it built in. So indeed, what the Luscher corrections are doing is correcting the beta ansatz point. So, okay, finally, the massless excitations in this case do not decouple from the massive sector because we needed to include massive massless scattering. So, future directions is a bit of what I already mentioned. Determine all wrapping Luscher contributions, perhaps from a TBA point of view. Analyze the massless TBA, in particular because when you have a mass and you have a procedure, an iterative procedure in the TBA that calculates exponentially suppressed and more exponentially suppressed contributions. For the massless case, you don't. So one interesting thing to do is, from the massless TBA point of view, to understand the magnitude of the contributions, which are not exponentially suppressed anymore, and the convergence properties of the massless TBA, to try and see if we can learn something, even if we don't know the TBA in this case, if we can learn something about the convergence of these higher and higher order corrections from Feynman diagrams. So another thing is, do these wrapping corrections play any role in the explanation between the mismatch of the dispersion relation in comparison to the BMN scattering? Well, it's a possibility, it's an open question, and it's definitely useful to look further into this, of course, because the same reasons that we've had problems here in figuring out this factor of 2, meaning one needs to have a very well set of assumptions to begin with to make sure that you actually can make a statement at the end about this. And this is all. Thank you so much. That the sum?
This comes from virtual particles wrapping the cylinder.
Yep.
So this was for ADS3 process 3 cross 4. Suppose that you repeat this calculation for ADS3 process 3 process 3 process 1, and then you blow up one of the spheres, you make it flat. Then there should be some sort of discontinuity precisely at the point where the sphere becomes flat, because new type of massless correction comes in. So can you use this sort of setup to get more information about these wrapping correction?
Actually, I hadn't thought about it, but actually that's a very good point, because what you could indeed do is to try and, before you blow up the sphere, you have some of the modes that you can actually have a tower of exponentially suppressed corrections, so you don't have this problem about all these corrections suddenly collapsing, right? And maybe you can actually look at the limit and see, again, how many will actually contribute, for example, and then I hadn't thought about it, but definitely it's a strong possibility of seeing this, yes.
Can you try to compute Luscher corrections for other solutions, not only SU2, but SL2 or short strings and so on?
Yes. And the answer is going to go like that. We don't yet have final results again. So there must be situations where some of these extra corrections that I was mentioning as from Luscher, meaning that you would need in general to consider all Feynman diagrams, and here it seems that you actually don't, that these number of diagrams that we used are enough. We are not sure that if this is the case for every solution. We guess it isn't, and we're somehow stuck in that problem, actually. I can't hear, sorry.
So usually, the Luscher correction can be obtained by using just power extension and powers of Y functions.
Yep.
And it is important, of course, that those Y functions are exponentially suppressed. They're small. So I was wondering what is the extension parameter with this?
So I don't know. You're saying if you don't have this exponentially suppressed, what is the?
Functions are not small. You cannot extend them.
So my whole experience at the moment has been just in trying to look at what happens with the massless TBA, where you can't expand, or you can expand, assuming an iterative process, and what you find is that you find some convergence, but just because the extra terms that you do in the iterative process are actually, I think what happens is that they're actually higher orders in J, in 1 over J. No, they're not exponentially suppressed, but they're still starting to contribute at higher and higher orders of J. So there is some convergence, but not the typical convergence you would need still to include.
So when functions are order 1 over J?
I would assume so. Up to the
overall coefficient. So that actually gives this idea that there may be some mismatch because of wrong extension to be because you do reproduce on
that's why.
So that may mean that somehow there's a different organization of your extension rather than 1 over G, more like string side where you have some capital. So that's actually quite striking that we get all the full functions into the same.
Yes, it was the first time we got it. We were a bit not expecting because we thought that other contributions should be there. We started thinking that maybe it's actually some property of the circular string solution that has such that any other contributions cancel out, or maybe there's a problem of expansions, of limit of expansions in J, but we don't. The answer is we don't at the moment quite know, because meaning it. Yes, it is the same form. It is not the same factor, and this factor of 2 is there for sure. So we at the moment don't have an exact way of explaining it.
It can't be normalization issue because you match incremental focus. Right? So some other paths match exactly. It's not just normalization.
Yeah.
Okay, so let's